Okay, thank you. Good afternoon, everyone. Sorry about keeping my coat on. I think I might freeze to death without it. Thanks so much to the conveners for the invitation. I'm really honored to be asked to talk at this session honoring Tapponnier. I actually never met him, but I knew of his work very well, especially in the mid-2000s when I was working on my PhD on the Southern San Andreas system and doing more active tectonics. And he, as many people have already talked about in the previous talks, he and his group were pioneers in understanding long-term geologic slip rates and developing methods for distinguishing them. And those of us working on the Southern San Andreas system at the time really took a lot of those techniques and learned a lot from what he did in Asia. But alas, my talk today is on subduction zones, and so I only have one slide that features Asia, so we'll go kind of different direction here. And I'm going to be focusing on the role of the subduction interface and the geology and rheology of the subduction interface and how it may help control parts of large-scale subduction systems. And this work is part of an ERC starting grant that I received in 2020 that's sort of winding down this year. And the grant was called Sediment and Subduction Interface Mechanics, or the SSIM project. And I was really fortunate to work over the years with many students, postdocs, and collaborators that are really great. And I'll be highlighting a lot of their work here. So the premise of my talk is based on sort of analyses like this one from Conrad and Hager in the 1990s that expresses subduction and kind of the kinematics of subduction as a function of an energy balance, where slab sinking is driven primarily by the potential energy of the subducting slab. And then, but that sort of potential energy is dissipated into three primary sources, among others, but these are the main ones, including the convecting mantle, including dissipation into slab bending as it tries to bend and subduct, and then including also the interface shear zone itself between the slab and the relatively rigid overriding plate. And so Conrad and Hager in that same paper came up with this kind of semi-empirical formulation where they could relate the convergence rate, a kinematic parameter, velocity, to these energy sources and sinks. So for example, the slab sinking is mainly due to thermal density contrast, so it includes things like density, the thermal parameters, the geothermal gradient within the slab, the length of the slab, and its thickness. And so many of those, of course, rely on slab age, so are related to slab age. And then the dissipation into the convecting mantle, they consider that some of the primary factors include, of course, the viscosity of the mantle, weak versus strong. And then this term represents just kind of the area of the convecting cell over which the flow is involved. And then they discuss dissipation into slab bending as a function of the slab viscosity, its thickness, and then the bending radius over which it attempts to bend. And then the part that I've been interested in is this shear resistance along the slab interface, which above the brittle ductile transition, you can think of as a sort of shear stress, and then below you can think of it as a viscosity, but you can think of it as an effective shear stress over the whole interface, or an effective viscosity, and it's a function of the length of the interface, which tends to correlate with the thickness of the upper plate. And so Torsten and Behr and I looked at this relationship in a paper in 2018, in particular trying to isolate the effect of the interface itself and try to put all the rest of the parameters aside and see how important the interface component might be. So we took some pretty reasonable assumptions for, say, upper plate thickness, thinking of a continental upper plate, slab viscosity, slab length, and plate age. And then these curves represent different thicknesses of the interface shear zone. And you can see plate velocity on this axis, and then interface shear zone viscosity normalized to the mantle viscosity here. And what this showed is a really simple calculation. It just shows that if your interface viscosity is really weak, say an order of magnitude weaker than the interface shear zone, then you expect maximal velocities. If you make it stronger and stronger, you can eventually perhaps jam subduction. So in that paper, we also wanted to look at sort of the flow laws that were available at the time to see what they predict about different geology or geological rock types, lithologies that enter the subduction zone and how they might influence this relationship. And what we found is that at least the flow laws available at the time suggested that all metasediments are generally quite weak, or the minerals that represent metasediments, say quartz, biotite, or a sort of schist of some sort, marble, and then also phyllosilicate-rich rocks like serpentine and tigerite, are all weak about an order of magnitude less than the reference mantle viscosity or the astenospheric viscosity. By contrast, we found that the flow laws available for metabasites were all quite a bit stronger, several orders of magnitude stronger. And so we suggested that this may mean that sediments in this sort of viscous sense in terms of their low viscosity can lubricate slabs and permit the maximum plate velocities, whereas slabs that are sediment starved, metabasaltic interfaces, tend to be sort of 1 to 2 orders of magnitude stronger and will decrease plate velocities. We went so far, this is my one Asia slide, we went so far as to suggest this might explain the acceleration of India with respect to Asia that seems to be documented toward the end of the Cretaceous, early Tertiary, with the idea that India was passing through sort of equatorial latitudes, and the equator today, and also likely then, has relatively high sedimentation rates, a lot of nutrient upwelling and biogenically driven sedimentation, and you also had potential sources from Eurasia and the Indian passive margin itself to deliver sediments, and that this may have been an explanation for how you could accelerate India convergence without needing large-scale plate reorganizations. So since then, for my ERC grant, I was still had some remaining questions, but wanted to keep kind of looking into this idea of sediment lubrication and how it affects plate speeds. So some of the main questions that I had included, what are the rheological properties of mafic subduction interface rocks? So really trying to understand better, especially things like blue schists, rocks, basaltic rocks change from blue schist and eventually to eclogite as they go down the subduction interface, and we had no constraints on some of the rheologies of these materials. I also wanted to try to understand how much the interface rheology actually varies in natural settings. So going and looking at sort of shear zones that are exhumed and tell us about subduction interfaces, how much variation do we see in where strain is localized or what materials are preserved there. And then I also wanted to look at time-dependent effects, so the effects of varying interface viscosity under dynamic subduction conditions, things that might include how it affects slab morphology over time, how it affects the way in which the slab interacts with the 660, how it influences stress distributions and topographic evolution in the upper plate. And then I'll show toward the end that we can go to 3D and think about long strike variations in interface rheology, which might be proxies for variations in sediment supply. So today I'm just going to sort of summarize what we found so far on these 3 topics. And I'll try to kind of convince you all that I think the interface rheology is a component of subduction systems and is affecting the subduction dynamics that we see in convergent margins. So starting first with better constraints on the rheology of interface materials. So as I mentioned, one of the key gaps that we had coming into this project was the rheology of blue schist, which there were no constraints on. They're difficult materials to work on. These are amphibole minerals, glaucophane, crossite, things like this, that you require relatively high pressures, but relatively low temperatures. So we did some shear experiments on glaucophane in my lab at ETH, and we were able to constrain both dislocation creep, a sort of power law viscous rheology, as well as diffusion creep, which is the linear viscous rheology for blue schist. And the details of these flow laws don't matter so much for this audience, but the main point is just that if we look again at the comparison to where we expect metasediments, maybe defined by something like quartz rheology, we still see that blue schists are several orders of magnitude stronger for the same temperature range, and then you jump up even more when you get to eclogite. So this is just confirming that mafic rocks really are strong in a viscous sense all along the interface at the temperature range where they're stable relative to metasedimentary materials. And this shouldn't be surprising for those of us who are geologists, because geologists have been describing sort of Boudin matrix relationships, one of my favorite French words, by the way, Boudin. Boudin matrix relationships from the shallow to deep interface all over for many many decades, really, where, like this example, you have basalt sort of rigid lenses embedded in a shale matrix. So in this case, the contrast is due to changes in both phyllosilicate and lithology, but also fluid pressures. And then, but we see this really commonly as well in deeper areas. So this is a blue schist facies Condrey Mountain schist in Northern California, showing these relict sort of blue schist and ultramafic lenses sitting in serpentinite and metasediment matrix. So it's not too surprising, but it's nice to have a quantitative constraints on those flow laws. Okay, so we see these contrasts in the field and we see them in the lab, but when we make these flow laws, they're of course end-member representations, but we know that subduction shear zones are often mixed. We often think of them as mélanges, my second favorite French word. And one of the questions we might ask is, do they really follow any of these end members, or is it more likely that they're sort of mixtures of these rheologies? And then another question we might ask is, well, since we have weaker material around, is it possible that strain is always just localizing into the weakest materials such that all subduction zones are uniformly weak and we should never expect the strong end members to participate? So we then wanted to explore kind of the distribution of these rock types and the potential matrices and the rheology globally, and the extent to which these subduction shear zones might vary in natural settings. So my student Elena Abila went through the literature, many 50 to 100 papers or so, to try to find examples of subduction shear zones that had well-constrained pressure temperature conditions, well-constrained sort of maps or cross-sections of block distributions, and well-constrained or good constraints on sort of the shear zone width that was participating. Those are pretty stringent criteria, but still she was able to find about 16 of them. These are the PT conditions of them. So they're from both sort of relatively low temperatures and relatively high temperature conditions. And right away, if we just look at the distribution of rock types within them, so she sort of broke them down into 7 potential rock types that we have good constraints on the mechanical properties for, so we can plug in the flow laws later that I'll show. But the main thing to see here is that there's significant differences from place to place in the dominant rheology, which we can think of as the melange matrix. So for example, several of these are schists, they're the gray. Several of them are antigrite serpentine, they're black. Several of them are aragonite. Some of them are even blue schist facies or blue schist mafic rocks. So right away we can see we have a variation in the types of sort of matrices that we expect. It's not just the weakest end members. So then Elena took each of these cross sections and she kind of digitized them with their block distributions and their shear zone widths included and their matrix material and their different rock types. And then she puts them with our colleague Jonas Rue. She put them into a sort of shear zone, and then she runs them a numerical shear zone, and she runs them under simple shear to reach a mechanical steady state, either in terms of constant viscosity or constant effective stress. So she doesn't need to run these for very long, maybe 10,000 years or so. So she did that for all of these subduction shear zones, and this is the compilation just in terms of viscosity here as a function of temperature of the shear zone results. And right away you can see that there's of course, there's a variation from about 10 to the 18 to 10 to the 20 that of course scales with temperature, where the weakest ones are the highest temperature and vice versa. But even at a constant temperature, say 500 degrees, we can see that there's a wide variation, more than an order of magnitude, almost 2 orders of magnitude in viscosity, expected viscosity. And that's due to differences in the matrix that host them, and also differences in the block distributions and percentages within them. So this illustrates that we really do have a variety, maybe an order of magnitude and a half of variation in natural subduction shear zones. They're not all concentrated in the only weak material. Okay, so we demonstrated that mafic rocks are stronger at all conditions on the subduction interface, and then we see that natural shear zones, as a result, have variations of up to 3 orders of magnitude if you include temperature, and about 1.5 orders of magnitude at constant temperature due to different matrices, widths, and weak to strong block ratios. So now we can kind of think about, we can use this information to populate models to look at sort of how this affects dynamic subduction. So one of the first ways we did this was in 2D models. We used the CIG code aspect. And we set these up. They have a slightly pre-subducted slab that's then decorated on the top by an oceanic crustal layer that we can change the viscosity of. And then we don't push these from the side. This is dynamic subduction. So this bit of slab basically drives slab sinking. And so then if we change the interface viscosity, we can view how that affects and its resulting velocity and other parameters. So here's an example where all we're varying in the model is the interface. So that crustal layer at the top is from 10 to the 20. These are linear viscous rheologies to 10 to the 18. They're all taken at the same time. And right away, you can see that this certainly has to have affected the velocity because the amount of subduction is quite different, with the really weak case having the most subduction and the strong case having the least. But it also affects slab dips substantially. So you can see the weak case has a much higher component of rollback than the strong case. And this affects then how the slab interacts with the 660. So in the strong interface case, you have a sort of penetration right through. In the case of the very weak slab, you have a lot more slab that is sort of above the transition zone, and because of the shallower slab dip. And eventually you might actually lie down that slab on top of the 660 as opposed to penetrating through at a more direct angle. If we look at how this affects the velocities, we can see it certainly does, especially in the free sinking phase. You have much higher velocities for the blue case, which is the weakest subduction interface case, and then the orange is the strongest. But this is not just the convergence velocity that's being affected. This is the slab sinking rate is faster, and the overriding plate migration rate, which we can think of as perfectly tracking rollback here because we don't have deformation in the upper plate. And then the ensuing convergence velocity is also affected. And you can see that that occurs early, pre-660, but also after the 660 at steady state subduction. You still have much faster velocities for the weakest interface case. And here's an example just showing all the data where we also varied slab strength, and just to make the point that it doesn't really influence slab strength very much. But you can see for all of these velocity metrics, you can see that both before the 660, you have a kind of linear increase with decreasing interface viscosity, and after the 660. We also looked at whether we could induce a sort of transient change in velocity by sort of inserting this kind of sediment slug you can think of, or just a thin strip that is much weaker than the rest of the surrounding oceanic crust. So this is a movie that you'll see that green strip enter the slab here, or enter the interface here. And when it does, the slab starts to shallow and you get much faster rollback, as well as slab sinking and convergence. And this is an example of just the convergence rate change, and you get this kind of Gaussian peak, basically rising relatively quickly over about 10 million years to the peak velocity that you would get from the uniform weak interface. So you can, in fact, transiently have a pulse of acceleration associated with features like this. Yeah.
I'm missing something. Can you explain to it why?
Why it increases in the case of the shallower subduction, or what?
Yeah. What causes rollback?
The angle of the slab and the fact that you have some force pulling it this direction requires that you have both. So it's not a perfectly straight slab, and you need to have a sort of force pulling it back in that direction. So all subduction zones that are not advancing will have some rollback, but it's much stronger here in this case. Okay, so next we wanted to look at what might happen in 3 dimensions and think about along strike variations in interface rheology, as well as look more at the stress distributions in the upper plate and the topography. So my postdoc, Derek Neuharth, he set up these 3D models that are similar to our 2D case, except that here he's just changing along strike the viscosity, so strong here and weaker there, and he kind of does various variations or pairings of these couplings of these viscosity changes. And this is to mimic something like what we see in Chile, but also other places. Here, the Papudo Seamount and the Juan Fernandez Ridge comes in, and there's a sediment-starved trench to the north and a sediment-rich trench to the southeast. So here I'll show a movie where this is a map view, and toward the front, including this one, will be the strong side, and toward the back is the weak side, which will also be this one. And then this is colored by the upper plate sort of stress regime. So blue is normal faulting, and red is where we expect reverse faulting. So you can see right away that the rollback characteristically ramps up here, so the trench is migrating, and that causes a whole rotation of the subduction vector, essentially. You get much more extension in the upper plate associated with the weak side, whereas the strong side generally, through most of it, remains in compression or neutral. You can see the stresses also represented here in the diagrams. And then you can see the slab morphology also changes in 3D. You end up with a sort of kink in the slab as part of the weaker part changes geometry relative to the strong part. Derek's also been looking at sort of how this affects topography. And what is kind of interesting there is here's a uniform interface where you get, as you might expect, a uniform trench shown here in blue, and then a relatively uniform 4-arc high and no real basin on the outside or on the inner part of the upper plate. Whereas when you look at the along strike model, you get a much actually deeper trench in the 4-arc region and also steeper 4-arc high. So you can think of this as you're changing in the strong side, you have much higher relief, and you actually have lower relief than the constant interface case in the weak side. So just to show what that looks like kind of quantitatively, here's the reference model where you have no along strike variations. The weak side actually shows lower relief, whereas the strong side shows much, much higher relief than the reference case. And then otherwise, he's found pretty similar results to the 2D models, not too surprising. A few interesting differences that I won't elaborate here, but basically, velocity increases as a function of lower viscosity, and then slab dip decreases with lowering viscosity. He's also looked at cases where he's sort of embedded a really strong interface between two weak areas, and you can see this sort of curvature develops, this kind of very arcuate looking subduction zone as you have rollback on either side, and you have really strong compression in the strong part and strong extension in the weak part. So you can get very distinctive along strike variations in normal faulting to thrust faulting to normal faulting again. Another interesting thing that he's looked at is just the average interface stress over the model duration against the horizontal compressive stress in the upper plate. And he sees a general good correlation between those two. But interestingly, the sort of homogeneous models have much lower stresses than the models with along strike variations. And the reason for this is that because you have weak material on the interface and strong material, the weak part actually drives faster subduction, and you therefore get much, much higher stresses around the strong domain than you would in a constant interface viscosity model. So to wrap up, I hope I've convinced you that heterogeneity in the form of subducted rock types is essential to subduction dynamics. We've been able to demonstrate that a low viscosity, if you want to call it sediment-rich interface, promotes faster subduction, trench retreat, and convergence. It enhances slab rollback and drives upper plate extension. It leads to shallower dips, generates lower upper plate relief, can induce trench rotations, and enhances interface and upper plate compressional stress in stronger regions. And I think this is interesting because it sets up these feedbacks between the processes that control sedimentation, which are usually things like changing climate, and also life can contribute to sedimentation rates, and then Earth's interior mantle and plate dynamics. And I'll just leave this up here for people to look at. These are just some thoughts on how we might try to test this with more observations in case any students around are interested in looking for projects. Thanks very much for your attention. I'm happy to take questions.